Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a third video in Indeterminate Forms and L'Hopital's rule for a differential calculus course. You should have already watched my videos on the Indeterminate Forms and L'Hopital's rule. From that point, we are ready to go. Let's go ahead and evaluate some limits using L'Hopital's rule. We're only going to deal with the two forms in this video of infinity over infinity and 0 over 0. As we move forward, we will have other forms we deal with, but you have to have these two forms down before you really can get into the other forms. So let's go ahead and start here. Evaluate this limit as t goes to infinity of t cubed plus t squared plus 1 over e to the t plus t. Now, prior to this moment, you would not be able to actually evaluate this limit. You would be kind of stuck because there's no algebra you could do to simplify this down. And this is critical to understand as you look back at what your abilities were and what your abilities now are. It's very, very impressive, all the stuff you've gone through. So as t goes to infinity, I hope you all can agree, this numerator definitely approaches infinity. And as t goes to infinity, the denominator, this guy right here, also goes to infinity. So this limit is indeterminate of the form infinity over infinity, and so therefore I can use L'Hopital's rule. And L'Hopital's rule just tells me that I could take that limit as t goes to infinity of the ratio of the derivatives of the function present here. So the derivative of the numerator would be 3t squared plus 2t. The derivative of the denominator would be e to the t plus 1. And you look at that and you say, great, L'Hopital's rule will allow me to evaluate this. And then you look at this and you realize you can't evaluate that because it's infinity over infinity yet again. Well, pretend this is a brand new problem and you were handed this. This is infinity over infinity. That's the indeterminate form of it. So therefore you should still be able to use L'Hopital's rule. And that is probably one of the most important concepts of L'Hopital's rule, is that you can continually use it as long as the limit continually becomes indeterminate form of infinity over infinity or 0 over 0. And as long as those limits exist. So here we have this limit. Let's go ahead and take its, use L'Hopital's rule to apply to this limit, so that we take the derivative of the numerator and divide it by the derivative of the denominator. The derivative of the numerator is going to be a 6t plus 2. The derivative of the denominator is e to the t. And again, we see this limit is going to be of the form, indeterminate of the form, infinity over infinity. Which means, yet again, we can run L'Hopital's rule. And when you run L'Hopital's rule, you get the limit as t goes to infinity. You can see, by the way, the complexity is reducing each time in the numerator because it's just a polynomial. So eventually you get down to this. Derivative of 6t plus 2 is 6. Derivative of e to the t is still e to the t. And that's going to be 6 over infinity or 0. That is the value of that original limit. It's just 0. And again, naturally, it is because the denominator is moving to infinity much faster than that cubic in the numerator. But you can't just say that and get away with it. You have to use L'Hopital's, not only in Calc 1, but Calc 2 and Calc 3 and so on and so forth. You can't just look at something and make a claim without justifying it. Moving forward, we have this limit as x approaches 1 of natural log of x over the sine of pi x. Now again, I look at something like this and I think, ooh, man, I don't know how I'm going to evaluate this because I need algebra to simplify this down if I cannot use direct substitution. If you try to use direct substitution here, you will get 0 in the numerator. Let me go ahead and just say this is approaching 0 because the natural log of 1 is 0. And if you try to use direct substitution in the denominator, you would get the sign of pi, which is also 0. So this is indeterminate form of form 0 over 0. If I could use algebra to simplify this, I would. Remember, always perform arithmetic before algebra, algebra before trig, trig before pre-cal, and pre-cal before calculus. So if I could perform a little bit of algebra here to simplify this, I would, but I just can't. There's just nothing that I could do. So instead, I just jump all the way up that ladder to calculus, and I'll use L'Hopital's rule because this is of form 0 over 0. And this limit will be the limit as x approaches 1 of the derivative of the natural log divided by the derivative of the sine of pi x, which is pi times the cosine of pi x. Every step of the way, you should try to use direct substitution. In this case, you can use direct substitution. So I use ds for direct substitution. That would be 1 in the numerator. And in the denominator, you get pi times the cosine of pi, which is a negative 1. And so this will be a negative 1 over pi. And there you have it. It's actually a really nice problem. I really dig that problem because it turns into something you would not have thought it turned into, especially when you're dealing with a 0 over 0 situation. A lot of people think that 0 over 0 will tend to 1 or something like that. But no, this tends to a number that's not equal to 1. It's in fact an irrational number, negative 1 over pi. So that's a good example of L'Hopital's rule. All right, let's see what the next example is. Evaluate the limit as x goes to 0 of 1 minus cosine of x to the 6th divided by x to the 12th. This is a fun problem in my opinion. It just takes a little bit of work. First of all, start with trying direct substitution. If you allow x to be 0, in the numerator you get 1 minus 1, which is 0. So I'm just going to go ahead and wrap that up and say this numerator is approaching 0. And obviously the denominator is also approaching 0. Now, I would love to use a limit property that we have learned in the past, but I can't. I cannot use it here. And this is a great example of the fact that you run into problems within calculus that require you to recall stuff from the past. In fact, I'm not going to tell you what the limit is. I was about to, but I think what I'll do is I'll move forward and then see if you catch it. And if you don't catch it, then I'll remind you when it happens. So right now I'm just going to say that's 0 over 0, which means I'm going to use L'Hopital's rule. If I can't use algebra to simplify this, I will use L'Hopital's rule. So L'Hopital's rule says that we are going to, because it's indeterminate of the form 0 over 0, we're just going to take that limit as x approaches 0, because that's what the original limit was. And we'll take the derivative of the numerator, which is a bit of a messy derivative, to be honest with you. Derivative of 1 obviously is 0, but the derivative of a negative cosine is a positive sign of its argument. And then you take the derivative of its argument, which would be 6x to the 5th. Downstairs, we'll take the derivative of x to the 12th, which would be 12x to the 11th. And remember, always perform arithmetic before anything else. So I'm going to go ahead and do a little bit of arithmetic here and a little bit of algebra as well, canceling. So this will be the sine of x to the 6th over 2x to the 6th. All right, so I hope that makes sense so far. At this point, I'm going to showcase something. I'm going to move that 1/2 out. Now, you could totally continue using L'Hopital's rule here if you wanted to. It is absolutely doable to finish this problem using L'Hopital's rule. But I want to remind you of a theorem from the past. The theorem is the following. The limit as theta goes to 0 of the sine of theta over theta is going to be 1. Notice that as x goes to 0, x to the 6th goes to 0. And so this limit could be rewritten as 1/2 times the limit as x to the 6th goes to 0, because again, as x goes to 0, so does x to the 6th, of sine of x to the 6th over x to the 6th. And that is exactly the same form as this theorem. And now you can easily see this is going to be 1/2 times 1. Now you didn't have to do it that way. You could have continued using L'Hopital's rule from this point. So I'll use a different ink for that, just to showcase that it would still lead to the same value. If you were to, at that point, try to use L'Hopital's, obviously as x goes to 0, sine of x to the 6 is 0, and 2 times x to the 6 is also 0. So if we were to use L'Hopital's rule at that point, you would get the limit as x is approaching 0 of 6x to the 5th sine, cosine of x to the 6th, all over 2 times 6x to the 5th. That's what the derivative of that denominator is. And you can see that the 6x to the 5ths cancel beautifully, and direct substitution can be used right here. Direct substitution, as x goes to 0, cosine of 0 is 1, and then the denominator is 2. And so you get the same answer. It's good to always keep in mind you have theorems you've learned in the past that you should be able to use. There we go. Now, as a final example in this video, you are being asked to evaluate this limit right here. Limit as x approaches 4 of x squared minus 16 over x squared minus 4x. If you just dive into L'Hopital's rule, you will see that this is definitely 0 over 0. However, as I've always mentioned, arithmetic before algebra, algebra before trig, trig before precalculus, precalculus before calculus. Rather than performing my calculus first, I'm going to perform some algebra first. This is the same thing as the limit as x goes to 4 of x minus 4 times x plus 4 over x times x minus 4. Notice the x minus 4's cancel, and now you can use direct substitution. So this is a lesson in, let me first evaluate that, that's going to be 8 over 4 or 2. This is a lesson in just following mathematics the way you learned mathematics. If you learned calculus before arithmetic, there are problems with you. But if you should have learned arithmetic well before you learned algebra, and then algebra well before you learned trig, and trig before you learned precalculus, and precalculus before you learned calculus. So doing all the previous stuff before you start doing calculus is critical, because it really speeds up the computations and actually makes things possible. This is how we evaluated this style of limit early on in this course without using L'Hopital's rule. And that's, you still want to hold on to those abilities. It's just very important. All right, that will round it out for this video. In the next video, we'll dive into evaluating or using L'Hopital's rule for different styles of indeterminate forms.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.